In this video, we've been going over some notes on waves. We'll talk through kind of like what the structure of a wave is, some examples of waves, and then in the next class period, we'll be talking about different types of waves. So for today, the first question on your note sheet asks you what causes a water wave, right? Like majority of you, when you think of a wave, you think of water, right? So what causes these water waves and why are they called waves, right? So they're called waves because they do have a similar structure to a wave in terms of physics. And a water wave actually is a good example of a wave. But they are caused by a disturbance of some kind, right? That can be the wind, right? The wind pushing against water. That can be, if we're talking about a really small pond, a really small wave, let's say you drop a pebble, right? And then that will make the ripple effect, the waves. So there's some sort of disturbance that's causing that water to not just sit flat, right? I mean, if there was no disturbance, right, like picture water in a water bottle, it's just going to sit there, right? And then you can shake it around and disturb it, and then it will create a wave. So when we think of water waves, they're created by disturbances. In the same way, a wave in science is really just a disturbance or something transferring energy, right? That's really what wind is doing there. It is transferring energy into the water, and then the water transfers the energy from one water particle to the next, right? That's exactly how a wave works. So a wave is really just a disturbance that transfers energy, and it does this without transferring mass or matter, and that's really important, right? For example, the sound that you guys are hearing right now is another example of a wave. In this case, I am causing, like, the vibrations in my throat and mouth are causing disturbances in the wave particle, or in the air particles, and that wave, that compression of air particles, is kind of how your ears are hearing this right now. So when you think of a wave, it's just really just a disturbance, right? And then it's a pattern to it, but it's really just transferring energy. So there are a couple of different examples of waves that I gave you here. Some of them I already listed out, right? Earthquake, water wave, sound, but there are a ton more examples, right? A slinky. I'm sure you guys have all had middle school science where they bring out a slinky and kind of like bring it up and down, right? Or like they compress it, right? A spring can be a common example. When you compress a spring, that's a certain type of wave, and then you let it go, and it goes back and forth for a little bit. Microwave is obviously a wave, right? Microwave. A radio wave would be another example. X-rays are examples of waves too. We'll talk more about those in our next class period. Light is also an example of a wave. It is a very weird wave, but it is another example of a wave. We will talk more about that and the complicated light again next period. But next, what is our general structure of a wave? So here I drew 3 different waves for you, and I think it's easy. Just like, waves are simple, right? I mean, it just goes up and down, right? I mean, we don't have to overcomplicate a wave. But at my 3 different examples I will talk through in a second. But first, I thought it was important that we go through some vocab. So on the side here, I wrote some of those vocab terms that you need to know. Crest. The crest is the top, right? It's the very top of the wave. Trough is the very bottom of a wave. I always think of trough like a pig trough where they're like eating all the slop, and it's kind of like basically just a big U, and then they throw a bunch of slop in there, right? So trough is the bottom of the wave. Crest is the top of the wave. Amplitude. This is the distance from crest to equilibrium or trough to equilibrium. Okay, so from one extreme down to equilibrium. Equilibrium would just be this middle point, right? Like, let's say this is a string, for example. Right, this is a string. If the string did not have a disturbance going through it, equilibrium would be where it was, right? Just chilling in the middle, just sitting there, right? My lantern's not a great example, but right, if I had it like this, with no disturbance going through it, that would be our equilibrium point, right? And then I can kind of put a wave through it. It's very terrible, but you can hopefully see the point there. So again, amplitude is one extreme to the equilibrium or the middle point. Wavelength is really simple. It's just the distance from one complete wave, right? The length of one complete wave. Frequency is just how often the wave goes by, so the waves per second. This is often used using the unit hertz. Again, that's waves, number of waves divided by the amount of time or seconds that it took, right? Period, this is a very similar term, but in this case, it's not how many waves go by in a certain amount of seconds or 1 second. This is how long it takes for one wave to go by. So slightly different from frequency, but both frequency and period are measurements of time, really. So I labeled those up here on the very top wave for you. I labeled crest here at the very top, trough at the bottom. Amplitude, again, I drew it from trough to amplitude, or trough to equilibrium, but you could have done it from crest to equilibrium as well. And then I showed you that this is one complete wave, right? One complete cycle of going up, crossing the middle, and then going down, and then again ending up at the middle. I think it's really important for you guys to remember, it's like one complete wave is not just like, oh, you went from equilibrium up to the top, down to equilibrium again. No, you got to go down and then up as well. So the second wave I showed you is just one more wave, right? In this case, though, it has a higher amplitude, right? There's a higher distance between the crest and equilibrium and the trough in equilibrium. Other than that, though, it's the same wavelength, right? And let's say that this dashed line is 10 meters, then cool, your wavelength is 10 meters, right? The wavelength for both of these is 10 meters. The amplitude here is very different. The second wave is significantly larger in terms of amplitude, but they are similar in terms of wavelength. The third example of a wave here I gave you, this is now two waves, right? We can see that it completes two cycles, equilibrium, crest, equilibrium, trough, equilibrium, and then back to crest, equilibrium, trough, equilibrium. Right, so it's two waves, and if it still takes 10 meters for those two waves to occur, we now have a wavelength of 5 meters, right? So we've changed our wavelength, which will obviously have an impact on our frequency and our period, which we can calculate if we were given a certain amount of time, right? Let's say that we for example, found out that it took 1 second for these two waves to pass. That would mean it would be two waves divided by 1 second. So you would get 2 would be your 2 hertz would be your frequency. And then your period, so the amount of time it takes for one wave to pass would be half a second. But next, before we can talk about different types of waves, we need to talk about our connection to sound, because you guys did look at those sound explorations from last week. And hopefully what you notice is that as you change the amplitude of the wave, right, how large it is vertically, as you're changing that, you are changing how loud or how soft it is, right? The higher the amplitude, the higher or the louder, the louder that the noise is, and the shorter the amplitude, the smaller the amplitude, the softer that the sound will appear to you. Pitch, right, how high or low something sounds, is based off the frequency of that sound. So hopefully those are things you started to kind of notice as you work through those sound explorations. But I really wanted to count on those now, or talk about those now. Next, so connection to previous units, so velocity and then energy. So first we're going to talk about our velocity. And this, again, might seem like a new formula, but it's really not if you boil it down, right? Because over here on the right side, velocity equals distance over time. In this case, for a wave, velocity equals the wavelength divided by our time, right? So we haven't really changed our formula yet. If you then go over to the left side and remember that frequency is the number of waves over seconds, right? Seconds is on the bottom here. Then really your velocity is equal to just your wavelength times your frequency, right? In this case, wavelength times frequency is really doing your distance, wavelength, divided by seconds, right? Because frequency has seconds on the bottom here. So really, ultimately, this isn't a new formula. It's an alteration of an old formula we've used tons of times, right? Velocity is distance or displacement over time. So this is really just us showing again, distance over time is velocity. In this case, being more specific to a wave, the velocity of a wave is just the wavelength times the frequency. And then finally, energy. As the energy goes up, or like that you put into the sound, right, or you put into the wave, or you put into the disturbance, right, the energy of that disturbance will increase the amplitude or increase the frequency. Okay, so again, like as you add more energy, you will hear it. The sound is louder or higher pitch. But really, that's how energy is at play here. So hopefully that made a little bit of sense. We're going to start to look at waves moving through different mediums when we talk about tsunamis and earthquakes in this Tsunami Interactive. We will talk about types of waves in our next unit. Please let me know if you guys have any questions, and have a good day, guys.